I'm glad to meet you all today for our webinar on tower site routing and switching. My name is Kamil Shamganov, and I'm Director of Engineering here at Winncom Technologies. And for a long time, routing and switching was one of my key specializations. And throughout my 15 years career at Winncom Technologies, I worked in different roles on hundreds and hundreds of network implementation projects. Starting from small office networks up to nationwide MPLS networks for some tier 1 carriers. At some point, I even invested a lot of my time and efforts to pass Cisco Certified Inter-Network Expert in Routing and Switching certification. And last year, Cisco surprised me with the notification that I obtained an emeritus status because I held that certification active for more than 10 years. Yeah. I feel dull. All right, so let's start. Very brief overview of Winncom Technologies, geography and what we do. We're a global distributor of wireless and wired network technologies with more than 15 international offices. We work with over 8,000 system integrators, value-added resellers, and service providers around the world. What makes us different from other distribution companies is that we are a very engineering focused company, and we always were. We're not only making sure that we have products on our shelves and deliver them in the most efficient way, we're making sure that customers succeed in their projects and order exactly what they need to do it. We know the products that we sell, know how and where they work, how to size, design, configure, maintain them. And on the US market, we distribute for over 70 manufacturers. We have 15 engineers on staff here in the US who have tens of years of field design and consulting experience. We have over 60 engineers worldwide, and we work together as a global team. And all our engineers are certified on expert level with product we worked with. And just to give an example, we have 6 Cisco certified Inter-Network Expert level engineers in our engineering team. So though many know us as a distributor of wireless broadband, is carrying products such as Cambium, Ericsson, Radwin, Ciplu, and CI, and so on and so forth. We're not carrying just radio products. We have everything one might need to build a complete network solution, including towers, enclosures, power, routers and switches, servers, monitoring and infrastructure software, fiber solution, and everything that needed, including passives and accessories. So what is more, being a distributor, we supply equipment for hundreds of projects per month around the world, and we're not just passing them through. Our engineering is involved in the majority of these projects, even if customers don't require that. We look through the BOMs order and make sure that solutions customers purchasing make sense and are configured properly. Of course, we're the first point of contact when customers experience any problems in their projects, and our engineering works together with customers to resolve them. So with all that said, let's proceed to our main topic of today's webinar, fixed wireless access tower site routing and switching. And even though we might be talking about general purpose routers and switches, tower site equipment for fixed wireless access networks has its own specifics. From the physical perspective, most of the tower sites are usually remote in relation to West Central Office, and sometimes require significant time to get there. Some of the sites might also have access restrictions, especially in situations with leased tower space. Another physical aspect is that often the environment on the tower sides is very far from clean enterprise grade data center. The dust levels, the airflow, humidity, temperatures often very far from ideal. So the equipment designed to operate in your typical data centers might not work well in such environments. From the perspective of performance and features, we're looking at relatively low performance requirements due to spectrum limitations we face in wireless side of things. And unless we're talking about millimeter wave fixed wireless access or new multi-user MIMO technologies, performance requirements for typical sites usually below 1 gigabits per second. And as tower sites and remote and often require long drive to get there, high reliability is the key here. So we also want our equipment to quickly adapt to link losses, flaps, and intermittent packet drops, reconverge as fast as possible to shorten service disruption. Of course, as we're operating in a public network, we want to protect equipment from potential security risks. So security on our equipment is also very important. Of course, last but not least is, of course, the cost. Fixed wireless access sites typically don't serve thousands of customers, right? Typically, we're talking about 100, 200 customers. So economies of scale don't really apply here. So we have to be very price cautious, and the cost of routing and switching equipment should be reasonable and affordable. So let's take a look at some of the components of typical WISP network. On the slide, we see typical design of a WISP network from components perspective. So here we have our access layer, that is entry point to our network. Then we have our core that typically consists of multiple components, such as aggregation, broadband network gateway, BNG, which terminates subscriber sessions, and border equipment that provides access to external networks. So this design shows functions for WISP networks. Actual designs of network might be different, but these components are always there in one way or another. So it doesn't have to be exactly the same design, but components are always on it. So let's take a closer look at each layer. Access layer, as I said, it's entry point to your backbone network. Devices in this level connect your fixed wireless access points and base stations to the network. They also connect some of the tower side peripherals, such as managed power systems, physical security gateways, out-of-band management gateways if needed. This layer also terminates connections to backhauls, and in case of redundancy, runs redundancy and convergence protocols. It also enforces some security measures to prevent unauthorized access to network and management interfaces, and implement basic quality of service functions such as traffic prioritization, broadcast storm control. So in this site, we see an access router that connects 4 access points, some peripherals to your network with the use of 2 backhaul links. So aggregation level is part of a network core. It terminates backhaul links from provider towers, aggregates the traffic from all of them, and provides high performance routing, switching between access network and upper level core components such as BNG and operation and management infrastructure. And depending on used network architecture and subscriber termination strategy, aggregation level might also perform tag and MPLS label manipulation to direct access network traffic to appropriate core components. Um, Broadband network gateway. This level is responsible for termination of subscriber sessions. The main functions are authentication, authorization, and accounting, AAA. Here you identify your subscribers, ensure authorized access to your network. BNG also serves as a first hop for subscriber devices. It's a default gateway for them. It often assigns customers your IP addresses and provides per user and per service quality of service, such as traffic shaping and policing. In a network where subscribers are assigned addresses from private IP space, BNG also might serve as a carrier-grade NAT device. So on this diagram, we see a typical design of the use of centralized BNG. Traffic from your access network is aggregated and delivered to BNG component, and it terminates and performs all subscriber management functions there. So the centralized BNG strategy allows you to utilize economies of scale and significantly reduce maintenance, as all subscriber-related functions are realized on the one centralized platform. Another approach would be to decentralize the BNG functions. Sometimes someone decides to bring it on access level or aggregation level, but this approach typically requires more maintenance and much harder to manage, support, and scale. Border terminates connections to external world, performs traffic load balancing between these connections, and in case of dynamic routing protocols are used to connect to upstream providers, these protocols are usually BGP. It runs the BGP protocol, announces local networks, and maintains large BGP routing tables. So let's take a quick look at basics, typical topologies. Topologies in fixed wireless access are very often dictated by geography and possibility to secure backhaul to desired service area. The bus topology is often observed in smaller WISPs when market requires network to grow in one direction away from central office. So it's basically a daisy chain of towers connected to each other. This is least favorable topology, of course, and there are many reasons behind it. First, the aggregated traffic from all towers is passing through the same backholding chain towards the central office, which eventually becomes a bottleneck. And also, it doesn't provide any redundancy, and failure of any site causes other sites behind it to fail as well. Star is also pretty common topology in smaller WISP. Even though it doesn't provide redundancy, it is better than bus because the link failures don't cause other towers to fail as well. And each tower gets its own backhaul to its expense. Then we have ring topology, which is natural evolution of a bus. In our experience, it is very rarely observed in WISP networks due to backhaul capacity limitations. So basically, to get from bus topology to ring, we just connect the last tower in the chain to central office, and then with that, we are getting redundancy and possibility to load balance traffic over two backhaul chains. And then, of course, have hybrid topologies, which are mostly observed in more developed WISP networks. And hybrids could be of many different configurations and flavors. They're often start as a star topologies, and then they have internal bus and ring topologies integrated in them. And these topologies usually introduce multiple levels of redundancy and require well thought out load balancing, convergence, and traffic distribution in case of network failures. Let's take a quick look at network design types. We'll start with layer 2 network design. This one is probably familiar to everyone. Classical flat design where equipment is connected to tower switches, and these tower switches are connected to other switches over some sort of a backhaul. IP addressing is not used to move traffic over the network, and all processing is based on MAC addresses and Ethernet frames. So from one single point in your network, you will see all the equipment as they would be connected to the same local switch. And you would use VLANs to isolate different types of traffic in this kind of network. So in simple network topologies, such as star and bus, this design is easiest to implement and makes a lot of sense. The problem with layer 2 protocols is that they don't like loops much. And without the use of special protocols, layer 2 network that has loop in it will almost immediately end up in broadcast storm. And the broadcast packets sent by devices will travel over this loop indefinitely, consuming all the network capacity, which results in complete network fault. To resolve this problem, majority of modern switches implement standard loop prevention protocols called spanning tree protocols. There are a number of flavors of these protocols with different specifics. Some of them are slower, some faster, some run as a single instance, and some can operate on a per VLAN basis. But the essence of these protocols is to detect loops and block ports that cause them. On that image on the left down, we see the typical ring topology where spanning tree protocol detected loop and broke the loop by blocking one of the ports. So it's good. It prevented the loop, but not necessarily perfect. So yes, we do have redundancy, and if one of the other links will fail, STP will detect it and unblock previously blocked port. The network will reconverge and all nodes will be able to reach central office. But if you take a look at the tower in the middle, it has redundant paths to central office. If one of the ports wasn't blocked, it could have had double the throughput towards the central office. You could have sent traffic in north and south directions, but layer 2 and STP with standard configurations will not allow that. And to achieve load balancing in this scenario, an administrator needs to separate traffic that needs to be load balanced in a separate VLANs, then turn on pair VLAN spanning tree on switches, and then set parameters in such way that traffic for one VLAN would go north and from the other go south. So this is pretty intense task, and it's becoming extremely complex in complex topologies. So it's practically unusable in complex networks. Yeah, layer 2 protocols were not designed for complex topologies, and in such topologies they are hard to implement and maintain. And what is more, STP protocols don't guarantee loop prevention, especially if loops are caused by devices not supporting these protocols. Right? If we connect some dumb hop to one of the switches on your tower side, it will cause the loop, and nothing will detect it. The whole network is going to be down, and it's going to be really, really extremely hard to find this problem, because in these cases, equipment usually becomes unresponsive You can't even log into the CLI. So in complex topologies, layer 2 works really bad. So our next design is layer 3 design. And I'm not going to touch the static routing design here. It's not scalable and doesn't work well in complex topologies. The typical layer 3 design involves the use of some sort of a dynamic routing protocol, such as OSPF or ISIS. And every network transport device in such network is configured with a separate IP subnet to connect to any other transport device. And layer 2 still exists there, but it's only exists on the segments between two layer 3 devices. So these are point-to-point links, and possibility of layer 2 loops are completely impossible. Traffic is moved over the network based on IP addresses, and dynamic routing protocols automatically detect network topology and provide each node with complete or partial picture of network topology, so it can make traffic routing decisions on its own. Such networks are much easier to troubleshoot than layer 2 with standard tools such as ping and traceroute. Routing protocols also provide a lot of useful information to troubleshoot and tune the network. Dynamic routing protocols are designed to support redundancy and load balancing. And if we take a look at the lowest router in the image below, with standard configuration without any effort, this router will use both paths to reach central office and will load balance traffic between these two links. And initial design and implementation of simple layer 3 networks is much more complex than comparing to layer 2. And in many cases, this design would be overkill for some simple topologies. And even though layer 3 is a much more sophisticated design and work great in complex topologies, it's not necessarily widely used in service provider environments. Now, the reason behind that is that layer 3, pure layer 3, wasn't designed with traffic isolation requirements in mind, meaning that all your interfaces, all your subscribers, all your infrastructure, everything in your network lives in one single routable space, and everyone can reach everyone unless you apply some access rules or implement some VERS, it's virtual routing and forwarding instances. And it not only makes implementation of multi-service services like a triple play very hard to implement, it also poses some security concerns. Another problem with layer 3 networks is that they dictate distributed BNG strategy, because you lose your layer 2 information from subscriber right on the access side. So you have to provide your IPs there. The gateway is going to be there, and some of the basic processing is going to be on the access side. So yeah, it enforces you to use distributed BNG strategy in most cases, or have partial functions on access level and then aggregation level. We saw that some WISPs, however, try to use pure layer 3 design, and then they become very creative in the ways they isolate traffic. But these designs usually have some pitfalls and make networks less secure, scalable, manageable, and maintainable. And the next level of evolution here is MPLS design. It combines benefits of layer 2 and layer 3 protocols and brings so many ways to innovate and deliver a wide range of IP services to customers. I would not delve deep into specifics of how MPLS works. I'll just talk about how it can make lives of larger WISPs much more comfortable and enable them to build redundant and reliable networks that scale. So in essence, MPLS runs on the same layer 3 network design, but some of the key features that it allows you to do is to overlay other layer 2 and layer 3 networks on top of your transport network. And if we take an analogy, MPLS brings to the networking the same benefits that virtualization brings to computing. So if before we had one PC with one operating system and we ran all our applications on it, all these applications existed in the same space, and if needed, they could have access to the same resources, same files. And with virtualization, we can run them in the separate virtual machines, so they wouldn't even know that they coexist on the same platform. And the same works with MPLS. So you run, so you have a layer 3 transport network that's available only to service provider infrastructure, and only infrastructure equipment is routed there. Then we tunnel other networks on top of this network, and these networks won't have any access nor to your transport network infrastructure, neither to any of the other networks that runs on top of that. MPLS can overlay layer 2, layer 3, and some older technologies like T1 or ATM even. But the most popular in WISP space is overlaying layer 2 networks. And a typical design assumes that subscriber traffic on access layer is encapsulated into tunnel and is delivered up to aggregation level. And aggregation level decapsulates it and sends towards BNG, and BNG then sees subscriber as it would have come from the pure layer 2 network. So it can perform all the functions it needs: authentication, authorization, and do it on a level 2 way. Since the traffic is tunneled and transported over your layer 3 based network, it receives all the benefits of layer 3 network, such as automatic support for redundancy, fast convergence, easy troubleshooting, load balancing, and so on and so forth. So it is, of course, much harder to initially design and implement MPLS network, but the benefits in larger complex networks are hard to overestimate. Such networks are easy to maintain and troubleshoot. It provides complete separation of user traffic from management and all other types of traffic. So resulting network is much more secure. MPLS also provides very powerful traffic engineering capabilities. An administrator can define which path exactly each type of traffic should take and what should happen in case of failure. And this actually happens really fast, in less than 50 milliseconds time. So which one is better? The answer is probably none. Each situation and each network is different. Layer 3 would probably be the rarest choice here for wireless internet service providers, because majority of wireless internet service providers, even if not providing multiple servers now, they plan to do that in the future. But yeah, sometimes we saw layer 3 networks working on WISP networks as well, and sometimes it makes sense. So here's some of our ideas and guidelines that we came up with by working with WISPs. Would not necessarily recommend startup WISPs to bother with layer 3 and MPLS at the starting stage. At that stage, it would be much more beneficial to invest in the subscriber acquisition and vertical assets and better backhauls. But it's still very important to design layer 2 network properly. And with proper network design, transition to MPLS could be a very, very easy process. You would need just to change transport network from layer 2 to MPLS, and the rest will stay the same. Proper layer 2 design in early stages could save a lot of time, and it could dramatically decrease the amount of problems and shorten service disruption during transition to the MPLS. And of course, if WISP network became large enough and current network design keeps it from providing better services, implement redundancy, load balancing, and so on, it must switch. Okay, let's take a quick look of on what Winncom Technologies offers for fixed wireless access market. We of course have Cambium with its relatively new CN Matrix products. We have MikroTik, which is a very popular platform in WISP market. We have premium carrier grade products from Ericsson. The products that power large tier 1 mission critical networks, but they're surprisingly affordable, and that's why I included into this presentation. They're very affordable, and WISP can afford it, can consider this equipment as well. And not necessarily relating to tower site routing, we have NetElastic, which is software-based BNG that can help you with all your subscriber management needs. So let's jump to the products. About a couple years ago, maybe a little more, Cambium, pretty well-known vendor on the market, came up with its own switching portfolio called CN Matrix. It was designed in-house, and it uses proprietary silicon to process traffic, which makes it very fast. All the products support layer 2 and higher models. The product also support some basic layer 3 functionality with the dynamic routing protocols. Switches they use the same software, which is binary compatible between all the platforms. And the main benefit here is that CN Matrix, it complements the whole Cambium ecosystem, which now includes some licensed and licensed backhaul, wide range of fixed wireless access options, indoor and outdoor access products, and now switches that connect everything together. And needless to say that the whole infrastructure can be operated and management within the same CN Master management system, which brings a lot of comfort to Cambium-based WISP. In a nutshell, there are two switch product lines, EX1000 and EX2000, with later being more advanced in terms of performance and features. EX1000 is available in 10 and 28 port options with and without PoE support, and EX2000 providing 4 port density options, 10, 16, 28, and 52 ports, also with PoE and without PoE support. Important to know here is that 16 port option supports 2.5 GE ports and PoE output of 60 watts per port, and it makes it capable to power some really power hungry devices. To the benefits, yes, Cambium indeed is one of the most known companies in that market. You can manage your whole Cambium portfolio from the same CN Maestro system. Switches are pretty easy to use and configure through quite intuitive web interface. And it also supports Cisco-like CLI. The price is pretty affordable for fixed wireless access tower site applications. And to the cons, it can only be used as an aggregation and access layer switch. Of course, no BNG or border functions are supported. Routing table size is relatively small, only 512 routes, which can cause some limitations if used in layer 10 networks. And again, what can you do with them? As it was already mentioned, access and aggregation for small to medium WISPs. And switches support per VLAN spanning tree, which allows you to do a manual load balancing in layer 2 networks. So you can start with the switches and grow to pretty decent sizes. MikroTik is probably one of the most used vendors in WISP networks. We design and build a lot of WISP networks for our customers based on these routers. And it is a MikroTik designed product. They don't use any silicon to process traffic. All the processing is done in general purpose CPU and software. Though with a modern massive core CPUs, MikroTik achieves very impressive traffic processing results. And due to the fact that MikroTik is a software platform, they can be very flexible on feature set, because you don't have to work with restrictions of your silicon. You can implement just whatever you want, and the processor will process it. All the routers we will look today support layer 2, layer 3, MPLS and VPLS features. The software architecture is the same across the router products line. Recently they released separate software for their switches called SWS. So we're going to quickly review 5 models that we often use in our designs. Let's start with RB11. It's a workhorse of small sites. We see them everywhere. It could be used as a switch. It could be used as a router. It supports layer 2, layer 3, MPLS, VPLS functions. It provides 13 RJ45 10,000 ports. It doesn't have any optical ports. So if you work with radios that require that, it's probably not an option. It provides maximum of 7 gigs of routing capacity, and these tests, they are done on a clean router without any configurations. Of course, as it's a software platform, the more complex your configuration, the performance drops down, but it's still pretty enough to serve typical fixed wireless access requirements. The next model is CCR 1009. This router is based on a different architecture. It's a tile architecture, multi-core processor. This one has 9 cores, provides more than twice capacity than AH1100. The same feature set. It supports 7 RJ45 ports, 1 SFP and SFP plus, which of course can be used to do optical connections. And this router works well as access and aggregation level device on small to medium sized towers. It can also be a simple border router when dynamic routing protocols aren't used to connect to internet. The next model is CCR 1016, 16 tile cores, pretty close to 1009 in terms of performance. It's higher by roughly 4 gigabits. The main difference is support of 12 SFP ports and 1 SFP plus. So this router is very useful in sites where radios are predominantly rely on optical interfaces. Besides being capable of running small, medium, larger tower sites, this router also worked well as an aggregation device for smaller WISP. We also used it successfully on as a BNG on the networks with below 1,000 subscribers. So the next model is 1036. Again, tile architecture, 36 cores. It's a natural evolution from previous 1016. Same functionality. Max traffic processing at 27 gigabits per second. Can work as BNG for up to 1,500 subscribers. And these numbers are based on our experience. Sometimes they can scale more, but it all depends on the number of features that are configured on a router. On that model, we have 8 RJ45 ports, 2 SFP plus, and yeah, as you probably know, this plus in the end means that it is capable to do 10 gigabits per second. And the last is 72 core. It's a flagship router by MikroTik. It provides 8 10 gigabit interfaces, provides maximum capacity of 78 gigs, and it can be used as aggregation and BNG device. It scales up to 2,000 devices. And this router also has enough capacity to perform BGP peering with internet service providers in BGP scenarios. As it was pointed out before, MikroTik is probably the most widely used platform in this market. Equipment works great on tower sites, has enough performance to fixed wireless applications, has rich feature set, and allows to be used in many any network design, be it layer 2, 3, and MPLS. Of course, it requires some good knowledge of a platform. Configuration process and UI is not very intuitive, and it's also not the carrier-grade platform. So please don't expect carrier-grade functionality and reliability. They're very affordable. They usually work great. They provide very high performance and generous feature set for the price. And what can you do with it? Pretty much everything. It works well in access aggregation, BNG, and border roles. And another manufacturer that we offer to our customers is Ericsson. And Ericsson has tremendous experience in radio and telecommunication world. Tier 1 carriers around the world use Ericsson products to build their high available and mission critical cellular networks. And in the past, Ericsson acquired one of the most successful players in MPLS and edge routing market, Redback. I used to work with that platform a lot, and it was really great platform at that time. So Ericsson used that Redback technology and legacy to build their new access and aggregation router 6600 portfolio. And routers in this portfolio are powered with Ericsson proprietary FPGA and silicons. It supports wide range of carrier-grade protocols, making it ideal for service provider applications. These routers feature Cisco-like CLI, and all routers in portfolio have the same feature set and differ only in performance, environmental characteristics, and port configurations. So let's take a quick look at what these features are. As I previously said, all the routers have the same functionality. the different performance port configurations and other characteristics. So in this presentation, we won't go to the higher models that offer hardware redundancy, as they probably will be too expensive for typical WISP applications. All the routers support a rich set of layer 2 functions and advanced redundancy protocols that allow these routers to successfully work in layer 2 designs. They also support very broad spectrum of carrier-grade layer 3 protocols and features that make them ideal solutions in service providers' networks. Support for MPLS and wide range of services that can be delivered on top of this protocol. And also, which is very important and useful in SP networks, it implements MEF compliant functionality. So this router is often used in telco environments with 3GPP technologies running on top of them. They support sophisticated time synchronization functions, and to protect the system from unauthorized access and encrypt the traffic, they support wide range of security functions and protocols. And another area where these routers stand out from other options is their support for QoS functionality, where you have many options to choose from to implement your traffic prioritization, shaping, and policing. Okay, let's jump into the products themselves. Router 6471. It's the entry-level router. As you can see, it starts with 30 gigabits per second of full duplex forwarding capacity. It scales pretty well when you add additional services and configuration because it's based on silicon and FPGA. The router is really small. It takes half rack space and features sealed design. It prevents dust ingress, which, as we've discussed earlier, is very important in WISP environments. Port configuration makes this router ideal for smaller sites and provides 4 SFPs, 4 RJ45, and 2 SFP plus ports. So the next one is this little 6371, which is outdoor version of previous router 6471. It features all the same performance characteristics, but can be deployed in outdoor environments with temperatures ranging from -40 to plus 46 Celsius. And needless to say that this router could be ideal in smaller tower sites that don't have enclosure or indoor space. Next router model is 6672. It provides up to 100 gigabits of forwarding capacity and can be used in large tower sites and aggregation applications. It has 8 1 gig SFP ports, 4 RJ45 ports, and 8 SFP plus ports. So the next level is router 6675. It's the last model that we will look at. The router provides 320 gigabits of forwarding capacity. It has 24 SFP plus ports that, with the use of right SFPs modules, can be configured to a wide range of different port configurations. It's worth mentioning that by default, all these 10 gig ports on all Ericsson routers are limited to 1 gigabit per second. And to unlock 10 gigabits speed, you need to purchase an upgrade license. And with this licensing design, we can start with 1 gigabit routers and then upgrade them to 10 gigabits. What are the benefits? It's one of the leading platforms in service provider market. It works great in many service provider applications. The performance of these routers is astonishing for their size. Routers have most of the features service providers might dream about, and the cost of these routers are surprisingly low, which makes them an affordable choice for WISP. If you would compare the pricing of these routers to comparable competitors like Cisco, so you would sometimes see a tenfold higher price tag. And of course, these routers are designed to operate in tier 1 environments. They have all the characteristics and functionality that larger carrier would like to see, and WISP, of course, will appreciate that as well. While these routers are designed to do access and aggregation functions, which they do perfectly, they can also be used in some border applications as well. They, of course, lacking any of the BNG functions. They just wasn't designed for that. This is carrier grade platform. The amount of features it supports, a number of ways you can configure them, is very broad, and it's just impossible to implement a comprehensive web UI interface to manage them. So these routers don't provide you with any web-based configuration experience. You need to understand Ericsson specifics and learn the CLI, which is pretty comfortable for anyone who is familiar with Cisco. So what can it be used for? As it was discussed, access aggregation and some border functions in a variety of service provider locations. It features premium layer 2, layer 3 MPLS, QoS, and security features for any WISP location for any size. Another manufacturer that I also want to highlight here, even though it's not necessarily placed in the tower side of things, but this is still one of the critical components of WISP infrastructures, NetElastic with its virtual BNG product. As we discussed previously, BNG function is to handle all aspects of your subscriber management. It terminates subscriber sessions, assigns IP addresses, serves as a first hop gateway, and applies and enforces per user and per service QoS policies, and sometimes provides carrier grade NAT functions. Even though BNG functions can be implemented with different level on a different level, you can distribute these functions on access. We saw these functions to be spread all around the network, where you would provide gateway and IP addressing on an access level. Then you apply and enforce the QoS policies on aggregation. So the centralized works much better, as it provides you with the economies of scale. So you have one single component that terminates all your subscribers, and you can, with the centralized approach, you can detach your subscriber management functions from the rest of your network, and you can manage these two functions separately. So it provides a lot of flexibility, allowing you to easily change access technologies you use to reach your customers. You can merge your multiple service provider networks together, and BNG functions and subscriber management functions will stay the same. So on this slide, we see a list of key features that NetElastic brings with this product. But what makes it different is that it's virtual. It's a software solution that runs on commodity server hardware, and with recent innovations in CPU and Ethernet adapter designs, this software solution performs as good as your traditional hardware platforms from Cisco and Juniper, and it does it at a much more affordable price. As I said before, the solution scales pretty well, and it's based on DPDK technology in modern Intel 10 gigabits chips. It can scale up to 128,000 of subscribers and 120 gigabits of throughput on one single server. And you can scale it even more vertically by deploying multiple BNG servers, thus providing higher capacity and redundancy. So here's the line card of features that NetElastic BNG supports, and I wouldn't go over all of them right now, as we already exceeded the time scheduled for this webinar. But you can always reach out to us if you are interested in any of the solutions we were discussing today, and we can have more detailed discussion and provide you with more detailed information about them. And with this, I'd like to wrap up the review of our products that we offer for Wisp Tower solutions. Let's keep in mind that besides offering the products, Winncom Technologies has tremendous experience in wide range of fields, and routing and switching is one of our strong sides. We offer a wide range of professional services and can help you in any stage of the project with our consulting, audit, network design, network implementation, and pre-shipment services. So yeah, if you have any inquiries, please reach out to your Winncom Technologies sales rep, and we will be glad to help you. And this is it. Thank you all so much for joining us today. I hope you enjoyed today's webinar. Stay safe and healthy, and have a great rest of your week.